And I'm coming from the north of Europe, Sweden. This is almost spring, if you wonder. This is not a hospital, it's a neighbor building. The hospital is a little to the left of the building. And if you ask that question, what do we breathe for? I would say that the breath adds fuel for combustion, oxygen. It eliminates waste products, and we think of carbon dioxide mainly. It can also participate in the regulation and the rapid regulation of pH. And in some species, it's important for elimination of heat, together with panting and having the tongue out. I don't see that many who do it among men, but it might be a possibility. But now, what about the fuel? I don't know if I have a pointer somewhere. So let us start with the fuel. I will focus on that. And I have got a series of figures from John Sheveringhouse. And if you go back to the early 18th century, there was a scientist called Georg Stahl in Germany who mentioned a substance called phlogiston. And this phlogiston was released by burning. And that somehow limited new thinking, because everybody thought that phlogiston, okay, but we don't know what it is, we cannot find it, but it does exist, obviously. So scientists, scientists at that time, they were to some extent blocked by this wrong theory. Now, there were, by the latter part of the later half of the 18th century, three independent scientists. One Swede, Scheele, an Englishman, this was Priestley, and then a Frenchman, Lavoisier. And in down here you see the possible year that they independently, more or less, of each other, realized that we have a special gas or a special substance, oxygen, that is what we are breathing. Priestley was considered to do that around 74, and Lavoisier later perhaps, and he was the one who finally demonstrated oxygen and hydrogen as parts of water. It started with that Priestley used a burning glass and used it to concentrate sunlight in a sealed glass vessel to heat mercuric calc. And that restored the mercury metal and released the gas that he could not identify, but it burst into flame. And he found that a small mouse could live longer in a sealed flask if it had this particular gas rather than air. And he contacted Lavoisier in 1774 and asked Lavoisier to repeat the experiments, because Lavoisier had a huge burning lens, and he did so using his huge machine to concentrate light and heat, initially for burning diamonds, but now to look for what is behind when you are starting a fire. And Lavoisier, he realized that Priestley's discovery was important, but he did not understand it because of the phlogiston theory that kept everything other thinking away. And he continued to call it eminently breathable air or vital air, but they also used the word oxygen, and oxygen means acid in Greek. And by the time, in 1785, 11 years later after Priestley's discovery, he could show that water was both hydrogen and oxygen, and that replaced the phlogiston theory. Now, back to my Swedish friend, of course, myself coming from Sweden, he sent a letter to Lavoisier, thanking Lavoisier for a book that he had got, and mentioned that he, between 71 and 73, had studied what he called fire air. And this is before the reports by Priestley and anybody else. And he asked Lavoisier to use his big burning lens to study the phenomenon. But Lavoisier never replied and has later denied the receipt of the letter. Now, coming from the same country, actually, I claim that he certainly sent that letter. Anyway, in the 1770s, these three scientists came to the same conclusion, that phlogiston had to be replaced by another theory, oxygen. Now, how much oxygen can we store in the body? I mean, if it is a fuel, it would be good, like a car, to fill it up and then be able to use it. But as you know, we can have only a small amount in the body, and we need to replenish or refuel almost continuously. And what this figure shows is one of many from a Canadian anesthesia journal, showing that this is the amount of oxygen that we have during air breathing. Part is in the lung, and in this example, the volume has been calculated to 2.5 liters, meaning that we have a rather small lung volume, like in anesthesia, even smaller in acute respiratory failure. And we have a certain amount in the circulating blood bound to hemoglobin, and a minimal amount physically dissolved in plasma. Now, if you hold your breath so that the transcutaneous saturation is measured to 90%, you can see that we have a decrease in the oxygen content. Now, if you breathe oxygen, you can increase the amount that you have in the body much more. If you have 2.5 liter lung volume, most of it will be oxygen. You will have a certain amount expired carbon dioxide that will, so to say, dilute the oxygen content. You can increase the hemoglobin-bound oxygen, but to a very minute amount, because you have perhaps 98% saturation here and 100% saturation there. So it doesn't make much of a difference. You will have more physically dissolved because of the higher partial pressure. Now, if you hold your breath and come down to the same transcutaneous or saturation, you will have the same numbers as you had when you hold your breath during air breathing or air breath holding. The difference will be the time it takes. So you will have a longer time before you come to the same saturation. And we did a study some time ago where patients who were anesthetized, they were kept apneic, and we followed how long time it takes for saturation to come down to 90%. The apnea tolerance time down to 9% during apnea. And those who had been got oxygen during the pre-oxygenation period, this is expired oxygen, so you are a little below 100%. They have this time to 90% saturation, around 400 seconds. If you do a pre-oxygenation with 80% and then hold the breath or apneic, you will lose a minute or 90 seconds before you come down to the same saturation. And with 60% pre-oxygenation, you are down to 200 seconds. Still quite a lot of safety margin, I would say. But what happens if we do an induction with less pre-oxygenation? This is 30% that we did in the study, Hans Roth and others, myself. You can see that if you extrapolate the line, you can see that the saturation will fall below 90% around 90 seconds, 1.5 minutes. And if you were to start anesthesia without pre-oxygenation, breathing air, I would say that it would take a minute or less before you have come down to 90% saturation. So then you have a very minor safety margin. You would benefit from having a higher concentration. The question is, do we need 100%? Can it be enough with 80 or even 60%? That is a question I leave to you. Now you can see that when you hold your breath with 100% pre-oxygenation, it takes a certain time with fairly stable saturation, and then it starts falling down rapidly, irrespective of you have pre-oxygenated with 100, 80 or 60%. And that is when the stores in the lungs have been more or less emptied, and now you rapidly fall when the oxygen is going down in the blood. So you have a limited safety at the same level as you started at, and then it will fall down. The fall will thus depend on the inspired oxygen, on the body stores, lung volume and blood, but also on metabolism. The higher the oxygen uptake or the higher the metabolism is, the faster will the fall in saturation be. So if you have a patient where you have a situation where you need apnea, a low metabolism or a quiet situation will prolong the safety margin during apnea. And the more nervous, anxious the patient is, the faster desaturation will occur. Now, how long can you hold your breath? We talked about normal people for a few minutes or 5 minutes perhaps, depending on where you start. But there was a spectacular show with Oprah Winfrey some time ago, and a person was put into a plexiglass chamber or acrylic chamber filled with water, and he could stay there for 17 minutes and 4.4 seconds, and then brought up alive, if I understand correctly. So you have obviously a margin if you are able somehow to consume oxygen at a low rate. I presume what he is able to do is to lower metabolism. I don't see any other possible explanation. He was breathing for 23 minutes, pure oxygen, but I don't see how much that adds after 5-10 minutes. But it might feel more safe to do that. But that is the upper limit. Now, can we go further and just let the breathing be? This is a paper among the first ones, perhaps not the very first one, diffusion respiration by Draper and Whitehead. And what that means is that they kept, in fact here, animals mainly apnoic, and then they can see how long can that be. But I'm not sure of results, but here I have a question. Is it that the mechanical ventilation of the lungs have become necessary in the course of evolution because the tension of atmospheric oxygen is insufficient for respiration by diffusion, or because oxygen there is diluted with nitrogen? Two possibilities. I think it was an interesting question, and then I tried to see, do we have any knowledge of what the oxygen in the atmosphere has been earlier? And there is a paper. So in other words, would these dinosaurs breathe lower oxygen or higher oxygen concentration? If it has been higher, can it be that we are fighting in a more severe environment? No, it is not. This is a little complicated, but it's an interesting paper that appeared in Science 5-6 years ago by Falkowski. Also Warren Sapel, an interesting guy who's done a number of interesting observations and studies. And what did they do? They followed for the last 205 million years, where they were not personally there all the time, but they have, by using different techniques, been able to trace the oxygen concentration over this period. And this is the Jurassic period, the Jurassic Park, the dinosaurs you saw, and we come then close to present time, the Tertiary period, that will cover the most recent 65 million years. And what you can see is that the placental mammals, they appeared about when the Tertiary period started. And what has happened over this period? oxygen is shown here. And you can see that it started around 10%, according to what can be found out by different techniques 200 million years ago. And then it has been increasing over time, so now we are at 21%. So we are not having a more severe situation regarding oxygen. And it may have facilitated the evolution of mammals. And the weight gain or the weight increase in mammals has been steadily rising over this period of the Tertiary era, and when we also have a steady increase in oxygen. So rather, we have a greater chance to cause or live on diffusion respiration rather than mechanical breath today than earlier. One has tested apnoic oxygenation and wrote a thesis in 1956 was Martin Holmdahl, who has been the chancellor or rector of the Uppsala University, old now, but a good friend to both Anders and me. He wrote a thesis in 1956, and he showed that you can keep animals, dogs in this case, on apnoic ventilation, apnoic diffusion oxygenation for quite a long time. I think in certain experiments up to an hour or so. And there will be an uptake of oxygen that will go on continuously if you are providing pure oxygen all the time in a pre-oxygenated lung. The problem is, of course, the elimination of CO2. Now, what he noticed, these are old papers and 56, but read this. In the case of 100% oxygen, that is the apnoic oxygenation, uptake of oxygen occurred during the whole apnoic period. Here about 10 minutes, but he has extended that quite a lot. But with 50% oxygen, the uptake of oxygen ceased after about 3 minutes. And with air, practically no oxygen uptake could be recorded after spontaneous breathing had been abolished. So obviously, with apnoic oxygenation, you have to give pure oxygen, but with the danger of providing high oxygen concentrations with the possibility of oxygen toxicity and any potential biochemical damage to the lung or to the body. One person who has been working close also with Martin is Anders, who introduced me. And he has asked the question, why does apnoic oxygenation fail with 50% oxygen? Is there any remedy? And he has done a number of studies, and one is recently coming out, or soon coming out, showing what I'm going to show in the next few slides. Why does it not work if we provide 50% oxygen during apnea after the initial 100% oxygen in the alveoli? What you can see here is that we start the apnea, oxygen is being taken up as in the Holmdahl experiments, but we will also get 50% nitrogen into the lungs, down the airways to the alveoli. And by the time nitrogen is concentrating in the alveolus, and finally, there may be no place for more oxygen at all. At this moment, there will be no oxygen uptake. So that is inevitable if we do it this way. Can we do it differently? Anders tested the opposite situation. If we have 50% oxygen and 50% nitrogen initially, before the apnea, and then we allow apnoic oxygenation with 100% oxygen, what will happen now? You can see that oxygen will be taken up, but there will be no further concentration of nitrogen in the alveolus, simply because we are not adding nitrogen. We will have the same amount of nitrogen that was there from the beginning. By this means, we are able to keep the oxygen at a certain level, 50% in this case, reducing the risk of oxygen toxicity. But CO2 again, what shall we do about the CO2? And then, of course, you can rely on extracorporeal CO2 removal. And Luciano has done a lot of work in that, going to Kolobov, who was a pioneer in this area, and we have Schiesenberger, who has done similar studies a little later. So, as you know, you are the intensivist, you have possibilities to handle also the CO2 accumulation. Whether you do it with extracorporeal measurements which may include oxygenation as well, or simply to remove CO2, allowing the apneic oxygenation to keep oxygen at a reasonable level. Now, is there anything else that can happen during apnea and the use of high oxygen concentration? We go back to a study where Lennart Edmark and myself were studying the atelectasis formation. Anders mentioned that we have been working in that field. And if you pre-oxygenate with 100% for just 3-4 minutes, you will see that all patients, in this case 16 patients here, developed atelectasis. If they were pre-oxygenated with 80% oxygen, they developed much less atelectasis. You see a big difference. And with 60%, we are close to nothing. And if I go back to the study with Hans Rolten in 1995, where we used 30% oxygen for 3-4 minutes and then continued that ventilation, or ventilation with that concentration, we saw basically no atelectasis. So there is a strong correlation between the pre-oxygenation and atelectasis formation that one may say should favor perhaps using little more moderate oxygen concentration. Again, I'm not the intensivist or the anesthetist, so I shall not make a recommendation, but you at least shall know what you are doing and the difference that you can see. Now, there is one more thing to mention, and that is if you use 8% oxygen during the induction, you get less atelectasis. But if you continue with 8%, you will be, by the time, develop as much atelectasis as when you pre-oxygenate with 100%. So what you actually do is to buy time. You will have time to make something. You can switch from your pre-oxygenation to 40% oxygen, that we do regularly. Then you will not see this increase in atelectasis. But if you continue, you will develop atelectasis to the same extent. It will certainly happen with 60% as well, although it will take a little longer time. So if you reduce pre-oxygenation, you will buy time, and then you have to do something that will prevent the atelectasis formation. Atelectasis, yes. This is an early study from 1984 or something, where you see what you may say is not that much if you are used to the ARDS CT scans that you have seen a lot of, not the least from Italy, Catanoni and others. But this is one of the first experiments where we see this amount of atelectasis in the bottom of both lungs after induction of anesthesia. You see the diaphragm that has moved cranially, and that reduces lung volume. And that is the major reason why FRC goes down during anesthesia to something very close to residual volume. When we did these first experiments, we could of course not take out the lungs to analyze them. What we did do in some were to inject radio-opaque contrast into the pleural space. So we could see that the densities were inside the lung, or at least above the pleural space. But we have to go to animals to really confirm our suspicion of atelectasis, or just learn what can it be. We did a number of different studies, sheep study among others, sheep in the front, and the CT scanner there, and they developed very little of atelectasis, so we moved by the time to horses. It was not quite clear what we were allowed to bring into the X-ray department, so we used black horses in the middle of the night. But we finally found that you have a varying amount of atelectasis. Man, awake, nothing, almost nothing at least, anesthetized, more than 90-95% develop atelectasis, but to a varying extent, from 0 to huge tissue volumes. It can be 25, 30, 40% of the tissue that is collapsed, and you may not notice it more than, it's a little more difficult to oxygenate the patient. Now, if you go to dogs that were frequently used when I started my research activities, dogs do not develop any atelectasis at all, and it's a very unsuitable lung model for lung function during anesthesia. It's sad to say when I go to the US and say this, because people don't like it, but this is an unsuitable model. If you go to the pig, you can see, not much here, a little atelectasis. Sheep, also some atelectasis. Finally, the horse or the pony, huge amount of atelectasis. I can add rabbits, and rabbits do develop atelectasis. So if you go to a plot between body weight and the lung volume, you see a linear correlation. This is a study where we have taken the figure, studied together with Villar and Kaczmarek some time ago. What is interesting is that the rabbit develops more atelectasis than the dog, for sure, nothing there, more than the pig, but not more than man, that is up here, and then horses up here develop a lot of atelectasis. We have not studied whales. But if we move on to animal models, I show you one line taken out from one of our experiments. Here without filling, here with the inflation of the lungs, and the question is, what species is this? It's giraffe. So it's a giraffe line here. And you may then know that they have long necks. So we have done studies on giraffe to study how big is that space and how is the matching of ventilation and blood flow. Here we get the giraffe. To be honest, this is not the same as this one. Here's my good friend Goran Nyman, a fascinating veterinarian, using a coloscope to look into the trachea of a giraffe. 3 meter long coloscope comes down to carina almost. So we have a long neck. Now, what do you think about that space in a giraffe? Huge? No, the giraffe has the same dead space or dead space ratio as a horse. And the horse has a shorter neck for sure. It simply means that the dimension, the lumen of a trachea in giraffe is much narrower than in a horse. And then, of course, you can say, but how can it breathe then? Well, it can, obviously. But you can learn a little about philosophy when you study different animals and species, because they have different solutions for different issues, problems, or whatever you want. The giraffe, I have learned, has no real enemies. It is not constructed to flee away from anything. It is moving graciously around among the trees on the plains and can eat the food high up where other animals cannot. And the lions who want to kill, to take a prey, a giraffe as a prey, has difficulties to reach the neck. And where to bite, by the way. Anyway, that was perhaps to say too much. But the wild cats and animals and so on, they are not attacking giraffe, except for sick giraffe. So they are safe, so to say. They don't need to breathe fast. That is the bottom line here. They can breathe quietly all the time. The horse is constructed to be able to flee and must have a very wide trachea and airways to reduce airway resistance. So that is why we have these differences in their upper airways. This lady, Göran, she's now preparing intubation of a lion. There's an elephant which has been studied. Now preparing a shot on a rhinoceros for further studies, but we have not studied with CT in these animals. So now I go back to man and effects of ventilation on ventilation and lung perfusion, and focus on anesthesia, because it has also a lot of relations to intensive care. If you look at the matching of ventilation and blood flow in the awake, healthy subject, standing up, so we have the apex and the base. Then we know from many studies from the 60s, 70s, 80s, John West, Permut, Michael Hughes, and so on, that ventilation, the broken line, increases moderately down the line. So we ventilate a little more with the lower part than the upper. Perfusion increases much more down the line. It may be absent more or less in the top, and then it increases down the line and will mostly exceed that of ventilation in the lower part. And this means that in the upper part, we have a little more ventilation than perfusion. The VQ ratio is above 1. In the middle, we have ventilation equaling perfusion, VQ equal to 1. And in the bottom, we have a VQ that is less than 1 because we have more perfusion. And we know that for optimum matching, we shall have a VQ around 1. If we have more than 1, it is a wasted ventilation. We don't need to ventilate this much because we cannot oxygenate blood more than we do with an EQ of 1. It is a dead space-like effect. In the lower part, where VQ is less than 1, we will have a certain impairment of oxygenation. So low VQ is 1 and the most common cause of impaired oxygenation in chronic obstructive lung disease, asthma, and so on. Asthma and COPD do not have shunt. If they do have that, they have a complicating disease. They have low VQ. Now, what happens with anesthesia? And I would say also in intensive care patients. And this is a study we did some time ago. A little complicated because I did a heart catheterization in my department. We moved the patient to the CT scanner. She was awake or he was awake. We did the CT scan and then anesthetized the patient. And this is a CT during anesthesia. Then we moved the patient from the CT scanner during anesthesia to another department where we had the gamma camera. And we did the gamma camera study to look at the distribution of ventilation and blood flow. And then finally, if there was still time left, we brought the patient to the operating theater. What you see here is that you have atelectasis in the bottom of both lungs, with some holes in it, okay, but you have atelectasis. And in this same patient, we have the distribution of perfusion down the line, from here down to here. And you can see that the perfusion increases down the line as it does in the awake situation. You have it reminding us here. But ventilation is very differently distributed. Most of it goes to the upper half of the lung, the open squares. So we have a lot of ventilation here, well exceeding that of perfusion. Then further down the lung, we have a decrease in ventilation, so it is less than perfusion. And in the very bottom, we have no ventilation at all. What is that? In the upper part, we will call that high VQ. And this will be measured as a dead space with conventional carbon dioxide or CO2 elimination technique. But this is not dead space. And dead space in itself, a real dead space, is not increased during anesthesia. But this adds to the wasted ventilation. But it is just high VQ. Then if we go down a little, or in the bottom, we have no ventilation, but we have perfusion. This is shunt, related to the atelectasis. So it simply tells us that this atelectasis does not open up during inspiration. We have it throughout the breath. That is why we get the shunt. But then interestingly, we have the region above the bottom, where we have less ventilation than perfusion, low VQ. What is that? And that is another phenomenon that we have known since the late 60s or 66, 67, and that is airway closure. You can see that if you breathe out, this is a pleural pressure of plus 3 centimeter water. That is at residual volume. Then you can compress the airways, because in the airway we have, let's say, atmospheric pressure, say 0. Plus 3 minus 0 means that you have a pressure that is compressing the airway. And that is airway closure. It is a normal phenomenon that we all suffer or enjoy from. You are free from it during a short period of your life, and that is when you are around 20. When you are younger, you have more of airway closure. When you get older, you have more and more and more. And I'm in the sad situation high up, where I have a lot of airway closure. It occurs here because pleural pressure becomes more negative higher up. And here we have a pressure or suction that will keep the airway open. If you inspire, and this is to total lung capacity, vital capacity maneuver, you open up all airways and the pleural pressure will be negative everywhere. So airway closure is a normal phenomenon that can be worse during certain conditions. And one is anesthesia. Why is that? And sedation. If you have a patient on ventilator because of ARS, whatever you would call it, you will have a reduced lung volume. It can be a baby lung in the most severe cases, but it has another background as well. But what happens when you have a low lung volume? You promote airway closure. Now, if you are breathing air or if you are breathing oxygen, you will have a very different effect on the formation of atelectasis. And this is shown here, if you can follow me. Here we have a patient awake. We give pre-oxygenation, either air or, that is no, well, it is oxygenation anyway, but this is air, this is 100%. We induce anesthesia, FRC is reduced, diaphragm is more transient, there's slight decrease in the diameter as well. So the lung volume is reduced and airways are closing, as I showed you earlier. Now, if we have air behind the closed airway, then the closure will not cause any other effect until quite a long time. But if we have oxygen behind the closed airway, then within 5 minutes the oxygen has been sucked up and we will have atelectasis. So the cause of atelectasis during anesthesia, and I would add strong sedation in a mechanically ventilated patient, is the combination of reduced lung volume and use of oxygen. This combination will for sure cause atelectasis sooner or later, and mostly very, very soon, within 5 minutes. So one should remember that. And in my opinion, the anesthetist and the intensivist is abusing oxygen. Good. Now, let me go back if I am able. Yeah. Is there any benefit of lung collapse under any condition? Well, perhaps not for a man, as far as I know. But if you look at this, another fascinating study with Goran, among others, Konrad Falke, Jesper Kvist from Denmark, and more people. They were staying in Antarctic for a couple of weeks. They drilled a hole in the ice far from where the ice, or where they had open sea. This meant that seals that were swimming under the ice, they came up to breathe at that point. Now they had an opportunity to catch seals. They put on different devices that made possible to measure physiological variables, the depth they were diving to, the nitrogen concentration or pressure in the blood. And then you can see here that when they were diving, these can dive to 300-400 meters. Here you have an example diving to 80 meters. And you can see then that and this is, I think, time. Here they are, the nitrogen tension in the blood is increasing, but when they are still continuing to dive, the tension goes down. And the sensor they had made a delayed response, so they have concluded that this peak is at 28 meters of depth. And that it's a high pressure, but if you take the air, the nitrogen pressure in atmospheric air and then multiply with the increase that is caused by the depth, you will multiply with 3.7, and that will arrive there. Now, to make possible a decrease in the nitrogen pressure means that they have to eliminate the source of nitrogen in the body, and they suggest alveolar collapse. So the diving bedeled seal can dive without developing narcosis or bends like the humans will do, because they develop complete lung collapse. And then, of course, they have to have oxygen stores in the blood and tissues that I don't know, but in the hemoglobin. So this is interesting. And it is my guess, but this is an extrapolation, that the whales, they have the same mechanism. And what are they then forced to do when they are coming up? When they blow, now I'm just on loose sand, but my guess is that what they do when they blow is to reopen the lungs. And they use a lot of surfactant, because we know that it's a foam, fatty foam, that is blowing out. Now to another extreme, and that is Mount Everest. We have some climbers, because we have talked about diving and the consequences for breathing and oxygenation. If we look at Mount Everest, the first report that I have is from 1953, and this is one of Tenzing or Hillary. We never know who was first, we can guess perhaps. The inspired oxygen tension on top of Mount Everest should be around 43 millimeter of mercury. If the arterial CO2 or alveolar CO2 is 40, then you will have no more than 3 millimeter of mercury oxygen. So it's an impossible situation. Only hyperventilation, reducing alveolar CO2 down to some 10 millimeter of mercury, would make possible to have an alveolar oxygen tension of 33 millimeter of mercury. Is this possible? Well, without or with the red Mao book. There is a rather recent study where they took arterial blood gases or blood samples on climbers on Mount Everest, not on the summit, but not that far away, 8,400 meters. And then they transported the blood samples down to Camp 2, 6,400 meters, where they could examine the blood. The summit is 8,848 meters. What did they find? Well, I'm sorry for a lot of numbers, but it's interesting. This is 8,400 meters. The PaO2 measured was on an average 24.6 millimeter of mercury. The PaCO2 was 13 millimeter of mercury. And then one should remember that the alveolar oxygen tension is 30. And that means that on top of this hypoxemic situation, you have a diffusion limitation by 5.4 millimeter of mercury. And we know that, that if you are breathing low oxygen concentrations, the lungs are not designed for that, and we develop a diffusion gradient between capillary and alveolar oxygen concentration. 5 millimeter mercury, which is not much, but terrible in this situation. To make things worse, this is a study. I was in San Diego when they were preparing for the American Mount Everest expedition in 1981. And this is a report by John West and a number of people. I know that Pete Sue was doing something spectacular at that time. When standing on the summit, 8,848 meters, he expired into a gas collector. And the expired CO2 concentration or tension was 8 millimeter of mercury. 8 millimeter of mercury. So even lower than on 8,400 meters. That means that with a tremendous hyperventilation, you are able, we can calculate the PaO2 to around 25 to even a little higher millimeter of mercury. So the limit for people who climb the Mount Everest, if they want to breathe air all the way, is to be able to hyperventilate. It might be the best test for climbers before they do it. The more you can hyperventilate, the better chance you have to reach the summit. Another thing is that with this blood gas, 25, 27 millimeter mercury, you can only maintain a basic oxygen uptake, around 200, 250 milliliter per minute. Any work, physical work, requires more oxygen, and they can take a few climbs, and then they have to rest. And that is well known. The last 100 meters will take them an hour or more, because they can only do one step at a time, recover before they can take the next step. Okay, that was perhaps a little of advice if you want to do it. Now, the very final thing is, if we go from very high levels, we go back to apnea. And then, because we are always thinking of apnea, but there's another thing, high-frequency breathing. I'm a little happy to show this, not only because of the lady, but this is part of their yoga, call it exercises, high-frequency breathing. And I had the opportunity together, well, I would rather say Claes Forsell and Jeet Pand, a Indian doctor, to study a couple, well, for jogging when they were hyperventilating or they were breathing at a high rate. This is somehow to get in the right mood before continuing other yoga exercises. And you can see what happens. The mean of these 3 or 4 people was that the resting breathing, 10 breaths per minute, goes up to 232 breaths per minute, and they can go on for an hour. 4 breaths per second. Then look at the minute ventilation. 6 liters at rest goes up to close to 100 or 94.5 liters per minute. The tidal volume, 0.8, goes down to 0.35. The dead space goes up tremendously, of course. And another thing that we have to consider when trying to understand why this is possible, oxygen uptake. Baseline 262 milliliters per minute goes up to 807 milliliters per minute. So before we had done this study, I know that people told us it's impossible. You cannot hyperventilate like they claim, doing it for many minutes, 1 hour, for example. But you can do it. And the reason is that their PCO2 does not go down. It's normal. How does it come? Well, I already pointed at it. The high dead space ventilation and the oxygen uptake, reflecting an increased respiratory work. This is transpulmonary pressure swings from resting 4 to 20 centimeters per breath. So by the hyperventilation that they are producing is simply a moderately heavy physical exercise. And by producing a lot of carbon dioxide, they are able to do this hyperventilation. And they feel good afterwards, they claim. So by this, I have come to the end of my presentation. And now I will recover or take it easy by sailing in the Baltic here, navigare necessest. And I thank you very much for having listened to this.